essentially, essentially, we have PhD students from multiple different disciplinary backgrounds, and they do quantum technologies. So I do the teaching. So I teach them all the basic stuff, make sure they're up to speed. I run labs with them. I also provide pastoral care. I organize events, and I do EDI work. EDI is very important to me. That's equality, diversity and inclusion work. And I believe that the only way to change academic culture is by, first of all, being noisy to the people above you and trying to change their minds about the way of things, and also supporting the next generation. And for instance, that is how I met Monica, because she was interested in a academic series, and she's a high school student. Could she understand it? Actually, yes. So we ended up communicating, and I went through my work with her, and since then I have been a mentor. Also, I love trains. You can ask me about trains if you fancy as well. So I did my undergraduate and my master's at Queen Mary University of London, which is in East London, and it's a lovely university. It's the only campus university in central London, so you can live on campus, so short walks to lectures. The department is highly regarded for its theoretical physics, especially in string theory and field theory. I did my master's in conformal field theory, and it was very mathsy. And the problem with maths, despite me being good at it, was that there was no point of just doing all this maths. There was nothing tangible to the real world. And so for me, when I was applying for PhDs to the field that I'd done my master's in, I was getting very disillusioned by just doing maths for the sake of doing maths. So I ended up going to University College London, where I did where I'm doing, or did, I'm in a weird trans stage, you know, where I don't know whether I'm finishing soon or not. So here I did my PhD in photoelectron holography, which don't worry, we're going to go into. And from there, I've done lots of teaching and lots of different roles, including being head of the Women in Physics group. And all of that culminated in me getting my job at the LCN, which is next door to the physics building at University College London. The LCN is also partly funded by Imperial and King's. So we are like this multi-university kind of facility. And we've got some amazing labs, so amazing that we can't actually have visitors in there because there's lots of secret stuff. So what is my PhD on? What was my PhD on? Well, it's on atomic physics. So that means they're super, super small. It's on light matter interaction. So light matter interaction is when we shine light on matter, things happen. That's just the basic of it. And we're going to go into what light am I shining, and also what matter am I looking at, and also what interactions happen later in the talk. So I specifically look at electrons. So I look at electrons only. I don't care about the ion, the middle part of the atom. And I care about a strong field regime, which basically means an infrared laser that's very powerful, got very high intensity. So not just a little laser pointer you can play with. The other thing is, when we talk about small things, and especially when we talk about electrons, things are quantum because they are quantum particles. I am theoretical, even though in this picture, I'm pretending to be an experimentalist in my partner's lab. I'm strictly theoretical, but that doesn't mean I haven't collaborated with experimentalists, visited labs, and also read papers and greater understanding with experiments, because the experimentalists show us what's actually happening in nature and we need to explain it. It's not like theoretical quantum field theory where there is no experimentalists about. This is a duality that you must work together. So in my field, you can do some very theoretical things like fake atoms, things that don't exist in nature, which becomes the heavily theory side. Or you can do the theory of things that do exist in nature, for instance, things that we would be able to do an experiment on. So I've done both. I've both done really crazy theory stuff, and I've done stuff that can be proved hopefully experimentally. And we will go into that further in the talk. So today's talk is about holograms of the fast and the frustrated electrons and lasers. I hope some of you get the movie reference. I don't know, you guys might be yeah, there's some nodding. Okay, good. I do worry when I talk to people a bit younger than me that they don't get the reference. So this is a hologram. So it's probably not what you expected. Probably some of you are like, huh, that looks cool. I would like that on a t-shirt. I've thought that many times. So what are holograms in atomic science? So we're going to cover that. Why are they fast and frustrated? And it's because of these dudes. It's because of the electrons and lasers. And as you can see now, lasers is our light and electrons make up the matter that we shine it on. So light matter interaction is how we get the holograms. What is a hologram? The dictionary says it is a three-dimensional image formed by the interference of light beams from a laser or other coherent light sources. I think that's a bit wordy, and I think it can be explained a bit simpler. So light is shone on a target. Light interferes with something. In this case, it's our electrons. Interference is reconstructed into a picture of the target. So we somehow, from shining a light onto a target, onto electrons, we then are able to reconstruct interference. So today we're going to talk about how do we actually reconstruct this interference? How do we know what's happening? So like I said here, the electrons interfere and they produce an effect that we turn into pictures. But how do we turn them into pictures? Because that's the complicated part. Also, I use the term target because it's a general term for an atom or a molecule. And the atom and molecule doesn't have to be real or exist in nature. When I talk about some specific things, I might name helium or neon or xenon, like specifically. But when I just say target, just imagine it's some sort of atom or molecule. So photoelectron holography is the posh name for what I do, because photo means the photons from a laser, electron means the electrons that we look at, and holography means that imaging thing I just talked about, which produces the patterns. So yeah, it's very, very simple, easy breakdown, but a really, really long word to write over and over again. So this is one of the tools that we use to look at the dynamics of the target. So that means basically, how does the atom move? What does the atom look like? Is the molecule chiral? Is the molecule, spatially symmetric? Just things like that. So we use the term dynamics. So here, this is essentially what we're looking at, is that we shine a laser on an atom, and then the electrons get disrupted by the laser and they fly off, and then at a detector, that black gate, we're able to reconstruct an image. And this image here is something that I can tell what an electron looks like. How does an electron interfere? I can see that there's some spirals and there's a fan pattern. I mean, this diagram makes maybe no sense to you guys, but for me, who's now done training in this diagram tells me a lot of really interesting things. So here we go. And then we go reconstruct an image. And this is called a photoelectron, once again, the laser and the electron. Momentum, because we record the momentum of the electrons. So the momentum they have during their time of flight, which the time of flight is their journey from their target after they were knocked out of the shell all the way to the detector. So why do we look at imaging targets? It's a good way to understand properties of atoms and molecules. We can then, once we know and we know how they behave, we can start editing them. We can start maybe changing the structure of some molecules, which could be really good for making food last longer or for medicine. Also, we can solve some problems, because at the moment we all want technology to be as small as possible. And when you make a transistor small, what happens is that the electrons, instead of staying in one place where they're meant to belong in a transistor, storing the energy, they end up secretly bleeding through, meaning energy is dissipated, which is the opposite point of a transistor. And that issue is because of quantum. So us being able to look at the way the electrons behave on the quantum scale will be able to aid us in maybe helping our technology become smaller and not have this problem of electron tunneling. Don't worry about electron tunneling because we will talk about it in a minute. The other thing is HHG, which is called high harmonic generation, and XUV pulses, something we're going to cover in this talk. And through the behavior of these electrons, we can actually create a more powerful laser, which is weird because we're going to start off with some very strong infrared laser, and then it knocks some electrons out. Some electrons do something, and then they're able to produce XUV pulses, which we could then channel into an XUV laser. And as you know, XUVs have much stronger energy than infrared. So let's answer our first question. Why is it fast? Well, we can look at on the pico and femtosecond, we can look at excitation of molecules and atoms, but actually the electrons in the atom, they move at attoseconds. All of their behavior is on the attosecond level. Attoseconds means 10 to the minus 18, so super, super, super small. And so that means anything they're doing is happening at 10 to the minus 18 seconds, so incredibly quick. So let's put that into context. 1 second to the age of the universe is what 1 attosecond is like to how we perceive a second. It is vast. It is incredibly small. It is one of the smallest things in nature that we can really describe. And that is the way that the reaction times that electrons have. So let's just do some little bit of maths. So if we imagine speed equals distance over time, an equation you have seen probably countless times, if we know that the time in which things react is in nanoseconds, we can rearrange this equation saying that speed is equal to some distance times 10 to the minus 18. And we know what atomic units are. So even if we put in the atomic unit in there, speed is still a huge number. So therefore, that's why it's fast. It's absolutely enormous and it's absolutely ultra fast. So that's why we say that this imaging process, this photoelectron holography, is fast because it is the way that electrons move. And the problem is our lasers are femtoseconds. So our lasers literally have to be timed right in order to capture the attosecond dynamics. So what do we call this field? Well, the lasers we use are called a strong field. So we also look at the attosecond scale, like I just told you. So I describe that my job as a theoretical attosecond scientist interested in the strong field regime. So that's what I do. I do attosecond because I look at the electron dynamics, and I particularly look at the way that they work in the strong field laser regime, as in I shine my special laser onto a target. And once again, 1 attosecond to a second, like how we blink, is the same as 30 billion years. So the life of the attosecond is just as blinking in the age of the universe. So why is it frustrated? That's the other question that we wanted to answer today. And I like to say it's because research is hard and it's very frustrating. But actually, that's not the case. Frustration is a very interesting phenomena that is in our world. So frustrated tunneling is one of many complex processes that the electron can experience. And right now, you guys don't even know what tunneling is. So we need to start at the very beginning in order to answer this question. First of all, what is a laser? I think all of you know that it's light amplification by the stimulation emission of radiation. How does a laser work? So what happens is some little photons move in a closed path, just around and around and around. That's not very, first of all, it's closed path. How are we getting the light out? And second of all, just a couple of photons doing this, that doesn't seem very strong. How is it meant to ionize my atoms? Well, what we do is we put in a gain medium. And so what happens is the little electron passes through the gain medium, and then it gets more, and then it passes through again and again and again. And so the photons just keep increasing, and they keep increasing energy. And therefore, we then, at a certain threshold, will be able to let them out. So in order to power the gain medium, we have to put energy in. And so then what happens is, like I said, at a certain threshold, the output beam can be released, which is then the laser that we use for our experiments. So as you can see here, you've got the original beam. You've got here those mirrors, the thing trapping the photons, and here you've got the crystal. And the crystal is that gain medium, the thing that increases the energy of the photons. And then finally, when there's enough, when we've reached that threshold, we can then shine our light. And this is just a tabletop laser, which you can sometimes find in schools or undergraduate university. So the other thing is about laser light is they can have certain polarization, so the shape of the laser light coming out. So linear polarization is just when the light acts like a sine wave or a cosine wave. Circular polarized light is when it has an equal distribution of sine components and cosine components in order to form a circle where it can just go round. Then whereas ellipticity is where there's where the amplitudes then change, just like an ellipse where you've got an A and a B, the different major and minor axes, you can then configure that number so that the light is just a off circle or an irregular circle, also known as an ellipse. So these are different types of polarization. Each polarization has a job. Each polarization is bad at something. And experimentalists and theorists know that certain types of polarization of light are really good for some things, but sometimes they're really bad for other things. For instance, linear polarization is really good at high harmonic generation, but because linear polarization is just linear, the type of high harmonic generation you get out is just the same. You can't vary it, you can't change it to make it stronger, you can't really control it. And circular polarized light is absolutely shocking. It doesn't even give you high harmonic generation. But when you combine two colors, so that means two different wavelengths of circular polarized light together and do a superposition, making a really fancy shape, like a 4-leaf clover or 3-leaf clover, you know, kind of like a propeller or a flower, that's really good for high harmonic generation. So as a theorist, we look at why a light on its own was rubbish, but then if you combine it with something similar to it, it's then amazing for a job. So polarization is important. So like I said, we've talked about what our target is, and it's atoms and electrons. Electrons are bound to the ion by the Coulomb potential. So they sit here on some rings, and they can't get any closer. They just stay at the distance because the Coulomb potential is holding them in. So the Coulomb potential is also known as the binding force, binding energy, because it's binding the electrons to the target's core. And we're going to talk a lot about the Coulomb potential. Next, these atoms then make up matter, as you guys well know. Everything is made up of atoms. Well, every molecule is made up of atoms, which then makes up our matter. So we've talked about the laser, and we talked about how does the laser ping off electrons. Well, we said that we have a powerful laser, but actually the laser isn't powerful enough to knock electrons out the shell, literally just knock them out. So how are these electrons escaping in order for us to read them by the detector? Well, we're on a small scale, so therefore the rules of the classical world don't live, and it's the quantum rules, it's the quantum realm. So we live in a classical world, and what our rules are is on based of what we can see. We can see visible light, we can see how that interacts with the world around us. For instance, shadows, that's a way of light matter interaction on a classical scale. But there is a subset of rules that are so special to the small scale, we've called them quantum. And we've had to make some mathematics in order to describe these quantum rules. And yeah, that's this is an equation which we use quite regularly in order to solve some of our problems. So how does quantum tunneling work? Like I said, there's the classical story and then there's the quantum story. So what we have is a ball, and it's living in this valley, in this dip, or in this well, whatever you want to call it. And we say that this well is how the binding potential is containing the electron. We say it's the potential well. So in order for the electron to be free, it must be able to climb that hill. So it needs a certain amount of energy to climb that hill. Like we said, our lasers are strong, but they don't have enough energy to push that electron out of the well and up over the hill, as in the electron away from the parent ion, away from the binding potential. Instead, this phenomenon happens where it just goes straight through, so that means it leaves, but it doesn't leave because it had enough energy. It's just left because of quantum. So let's talk about this more in the terms of our story. So here we have the electron, and it is bound to the ion because of the Coulomb potential. And like we said, we represent it as a well that it has to overcome. So here is the parent ion, so the ion that belongs to the target. And here is that little electron sitting in a well, unable to escape. We have this thing called IP. IP is the energy that's required to move the bound electron, as in just this electron, up over the well and free. And like we said, the IP of the laser is not enough. It's not enough to get that little electron out of the well. So now here comes the laser. The laser stimulates the electron. The laser shakes the Coulomb potential. It rocks the entire potential. It changes, it interacts with the energy that binds the electron. And in that moment, the electron can break free and leave. So this is what we call quantum tunneling. What happens is the laser does not have enough energy to get the electron out the well, but it has enough energy to disturb both the electron and the binding force, which allows the electron to make its escape. So the question is, where do electrons go? So once they've tunneled out away from the parent ion, the target's core, where do they go? They can go anywhere. They're free now. So they will make a journey to a detector, and the detector will record its momentum and its time of flight. So at what time did it leave? What time did it arrive? What momentum did it have in the beginning? What momentum did it have in the end? But that's experimentalists. I don't have the luxury of a machine that does that. The machine I have is a computer. So I need to know the mathematics behind how the electron moves in order for me to code in the mathematics so I can get some data out of those things like time of flight and the change in momentum. So the thing is, electrons just don't directly just go to the detector. They're not well-behaved particles. You've just seen that they're able to quantum tunnel through things. They don't just want to go straight to the detector. They want to have a journey. They want to do something during their freedom. So we call the path that electron takes trajectories, and the route and time it takes for them to arrive at the detector is really important. It tells us where the electron lives in the target. So if you have a target and a laser, and if an electron takes a longer path, we know that it could have been living at the back of the shell. If you think about it on a 2D plane, it could have been living here rather than living at the front. So that's something that we can tell, and we can then identify the structure of what these molecules or atoms look like. So once again, imaging. So we can also say how fast the electron travels at various stages, which tells us the binding potential of the target, because there is a transfer of energy and therefore there will be a transfer of momentum. We also look at the various forces at play, because sometimes electrons get pulled off their path. Why do they get pulled off the path? What's happening there? And that means we're able to define the Coulomb potential and its quantum behavior, because the only forces that are at play here are the laser that takes the electrons away and the Coulomb force that's trying to hold on to the electrons. So that's the question, is how can we tell the different paths apart? So I classify my paths in a very special way. We say that after the detector records the information, I know that there are certain values or thresholds which mean different things, and this allows me to classify my electron behavior. So once upon a time, we said there was two types of paths: direct, where the electron would head straight to the detector, no questions asked, and it would go straight there. The other one is rescattered, where the electron on its path would cross back over the parent ion, cross over its original target, and the Coulomb potential tries to drag it back in. And it drags it back in such a force that it recollides with the parent ion and then zips off again, heading back to the detector. So we call direct, straight to the detector, and we call rescattered when electrons return to the parent ion, feel the force of the Coulomb potential, and then head off to the detector. But actually, there's three types. There's something called the hybrid, which we'll go into detail in a minute. But the hybrid is where it feels the force, but it doesn't feel the force. So like I said, for the direct path, laser tunnels the electron. Electron is free, gains energy, electrons move to the detector, no deviation. So let's pretend here is our core, here is our electron, the laser comes in, electron goes to the detector. No trouble, nice and simple. So once again, we then have the rescattered or the recollision electron path, where the laser tunnels the electron is free and gains energy. And the way it gets caught up in the field is it might go past the parent ion, meaning that it's close enough, it's in a range where it can be drawn in by the Coulomb potential. And in that drawing in of the Coulomb potential, it then rescatters off and then heads off to the detector. Then finally, the hybrid electron path is where the laser once again tunnels the electron's free and gains energy. But the electron comes near to the parent ion and feels the Coulomb potential. It doesn't come close enough where it's dragged back and then rescattered. It just slightly feels the Coulomb potential. So it ends up having this little wobble, a little bit, do I get drawn in? Do I not get drawn in? And those paths are particularly very interesting, because the question is, why was it close enough? What does close enough to the core mean that it isn't dragged in? What are the constraints that allow the electron to be wobbled and feel the Coulomb force, but not be fully dragged in to be rescattered? So this is now the part of the talk where I talk a little bit about my research and how I undertake things and how I do things. I like lots of things in my research. What I like is targets to be exotic. So I like them to be different shapes. I can code them to be different shapes that don't exist in reality. Or I can use these guys. These are excited states. So different variations of the same atom, but they're in different energy thresholds. So they can end up looking like dots or donuts or flowers. And when you shine a laser on them, because of their different geometries, things get a bit interesting. So I like looking at the tricky paths, those rescattered and that hybrid path, because the direct is boring, the electron is just well behaved and just heads to the detector. These involve that darker force of the Coulomb potential and questions like, why does this happen? What are the thresholds? Why does it happen sometimes and not all the time? And I also like looking at the exchange of energy. So when that moment, when the rescattered electron comes back and hits the parent ion, what happens? Because there definitely is an exchange of energy, and what is released? What happens there? And actually, we're going to talk about that in a second. So we say recollision when the electron hits and then goes away, and recombination when it hits and then there's an exchange of energy are the fates of the returning electron. So this is the three-step model. It's simply what I've told you. Electrons tunnel, electrons accelerate in the continuum. They then re-enter the fields of the Coulomb force, and they then ping back off to the detector, or they recombine. And recombining is when they release the energy exchange. So like I said, when they recombine, what does that happen? What does the energy exchange mean? It means that the electron's energy is such a high threshold that it will, in fact, in its reaction with the parent ion again, it will release a photon. And this is what we call high harmonic generation. That photon is actually so energetic that it's in the XUV range. So we're going to talk about high harmonic generation now, because this is something I study in particular. So like I said, we just have the same setup, tunneling, acceleration, and we look at the moment that it recombines, the exchange of energy, and it emits an XUV photon. Low energy photons give us high energy photons. So here, if you look at wavelength, and you then look at increasing energy, you can see that there is a inverse relationship. So that means that because we're going to be looking in this range, the wavelength is far different to the infrared, and the energy is far greater. So that's why it's this really nice process of, we take our infrared laser, watch all of these electrons rescatter and recombine, and the product we get of that is this XUV range, a much higher energy. And then with higher energy, we're able to then do more things. So for instance, make photoelectric cells and improve them, because obviously this is in the ultraviolet range. And also we're able to then shine it on more targets and do more interesting things, because at the moment, the power in order to generate a laser from scratch that's in this wavelength or in this energy range takes a vast amount of energy and vast amount of room space, and actually isn't a sustainable process. So here, like we said, is we put in the red light, and then what happens is the electron isn't ejected. You know that the electron has been ejected through quantum tunneling, but just in general, red light does not have enough energy, whereas violet light, XUV light, actually has enough energy in order to circumnavigate, to not even undergo the quantum tunneling process. So here, if we were able to put two red photons together, we get one violet photon out. So if we continually shine red photons, as in our infrared laser, we would then be able, we'd be able to get a pulse of this XUV continuously. And here is what we do, and this is what we do with our system. So like I said, we have our standard red laser. It then shines into a target. Our targets are usually gas in experimentation. And then through that recombination, recollision process, you can see that here, there is an XUV radiation. And you can see that it's both blue and red, because of course, the original laser is still shining through. So here, we get the XUV and the original infrared laser out. So sometimes we have to put filters, like this little filter here, which means it will take away the infrared laser. And it means we can just have the pure XUV laser as our product, which we can then use for other things. Here, once again, you've seen this before. This is just the potential wow. Here is the electron leaving. Here is the electron moving around once it's been released by the laser. And here it is recombining, and that's when it releases the XUV pulse. So the question is, why do we bother doing this? I mean, why do we bother doing any research? What's the point? Like I said, this allows us to get to know materials better. It allows us to look at what timescales this is all happening on. And it allows us to do it at an attosecond level. So like I said, we can use these further XUV emissions for future experiments or further experiments. So now we're going to finally answer the question that we started with. Why is it frustrated? Well, actually, it's not that hard why it's frustrated. You remember this guy, the quantum tunneling. So what happens is, regardless of the fate of the electron, tunneling happens. And there are quantum effects due to the ionization, and the electron escapes the parent force, as you have seen. So regardless of anything that happens, tunneling is a consistent thing that will happen, because that's what allows the electrons to escape the parent ion. But if we're talking specifically about high harmonic generation, the specific fate of an electron, we suddenly call quantum tunneling frustrated tunneling. Even though it's the same tunneling process that the electrons that move direct to the detector feel, we just call it, for some reason, frustrated tunneling, only for when we talk about high harmonic generation, which is, I think, is silly, because all tunneling is all tunneling. But there we go. That's why it's fast, and that's why it's frustrated. So how do I get results? And the how I get results is, well, there's a lot of theory going on here. I've told you a lot of processes that have happened, and each one of those processes contain an inordinate amount of mathematics. So what happens is, I break down the theory, I translate it into mathematics. I then use the maths to code a program, and I build a program structure. I then put in an input file with various parameters and conditions. So for instance, my input file might say, I want helium, and I want the laser to have this wavelength, and I want the wavelength, the intensity to be this of the laser. Oh, and I want the helium to be placed this far away from the laser. And then I can click go. And then all the math starts to run, and I end up getting loads and loads of files of path 1, path 2, path 3, all with different momentas and times. And then that is my information about the electron. So that's what I do, is I build up all this mathematics slowly into a program, and then I put in an input file, and the input file has lots of different things in it. And then once I run it, I'm able to then plot diagrams. So how does an experimentalist get results? Just before that, we're going to just answer some questions that I was given that I hopefully have either shed some light on or go into more detail. So in both theoretical and experimental, there is a lot of data collection. For me, it's easy. I just have to write a code, put in a few numbers, and then my computer collects the data for me, and then I can then plot it into diagrams and do my own analysis. For an experimentalist, they have to run experiments over and over again, put the helium gas in, shine the laser, get the information, put the helium gas in again, shine the laser and get the information, because they need multiple statistics. One run is not enough for experimentalists, because the experimental process is so tricky, because you've got to do things that are at cold temperatures, and you've got to rely on machines that break and that are fragile. And also there's environmental conditions that can disrupt the lab too. Whereas me, I just have my computer. So like I said, an example of my process is, the other day, I decided that I was very bored of having linear lasers, remember linear polarizations, in my code. So I coded in the option to have a circular polarized laser. So I coded that in, I put in, you know, sine plus cosine with all the right things. And then after that, I then put in my input file to select the circular polarized laser. So I was able to do the helium again, but with a different laser type. And I was able to then compare the results and see what's going on there. I'm lucky that I've got a code that's very well managed and is historic through different people in my group. And I've made my adaptations and other people have made theirs. But to form a code like that, it is no simple task, because not only have you got to think about the complex mathematics and the cases, you've also got to think about some of the quantum behaviors which can cause mathematics that can't be solved. So you have to sometimes do numerical solving rather than analytical. So what's my use of this physics in atmospheric physics? So I'm assuming atmospheric physics is the physics of rain and weather, things that go on in the atmosphere. It's funny enough, is when you first think of that, it's no, I shine lasers on targets. Actually, in atmospheric physics, you look at the way that XUV, as in from the sun, interacts with our world. So whether or not that will be warming things, or you know, skin cancer, or looking at photoelectric cells and, you know, solar panels. Our work replicates that, because like I said, we're creating these XUV pulses. And so replicating them in a more consistent way than they do from the sun also shows us that the way it interacts with the world too. So in a way, we can simulate the sun just with this laser setup. So at first you might think there's no connection or that there's very little, but in fact, we're kind of mirroring one of the key things is how does XUV travel through an environment. So what kind of mathematical and computational methods do you use? So a lot of this is quantum. So there's something called integrals, which looks at the area under a curve. So if you imagine integrating, so you've probably learned that when you have some sort of distance, you can differentiate different distance to get a velocity, and then from that you can differentiate to get acceleration. We also use integration because actually we know the acceleration, but we want to look at the speed or the momentum or the distances it travels. So we do a lot of integration. The integration is also complex, both in the terms of how difficult it is, and also in terms of types of numbers. So what happens is we actually see that we deal with time that has complex of components, so it has an imaginary component. We also look at the action, and we do the steepest descent method, or the saddle point approximation. So we have lots and lots of very complex mathematical ways in order to solve the information that we're given, because unfortunately it isn't just a case of an energy exchange. We've got to actually deal with the fact that these electrons feel different forces at different times under different circumstances, and they are in fact quantum particles. So as for computational methods, I code in C++. The reason I code in C++ is because the code I got was historic, and when I went to my undergraduate years, we were taught how to code in C++. Don't feel that you need to know how to code in C++ to be a scientist. C++ is dying as a type of coding language in terms of science. It will always be used in particle physics, so anything like that CERN does, because C++ has the advantage to take high amounts of data. And so yeah, that's something that I use. And then I also love Mathematica. Mathematica is great for solving things analytically. And like I said, sometimes you can't solve things numerically, as in just plugging in numbers, getting numbers back out. Sometimes you have to solve equations backwards in order to get some numbers to put them in numerically. And Mathematica is such a strong tool for that. Also, it's phenomenal for plotting as well. So it means that I can do some analytical work with my data that I get from my big C++ code. I'm able to then change that data into the format I need through analytics, and then able to plot it all in one program. So I highly recommend learning Mathematica and using Mathematica, because it's used anywhere in physics and engineering and the mathematical sciences. And it's in its name, it's Mathematica. So why is my work theoretical? Well, like I said, the university I went to provided experimental stuff, but I just wasn't interested in that. I like theory because I'm good at maths, and I'm interested in explaining the world through a different language, through symbols. So that's why my work is theoretical, but like I said, there are experimental methods. So I'm going to talk about one experimental method just very quickly, and that's called cold trims. And cold trims is what actually my partner uses in his lab. And it's cold target recoil ion momentum spectroscopy, where that essentially says cold target, it's going to be a gas. The target's going to be in a gas form, and the gas is going to be cold. That's all that means. Recoil, you guys know that the electrons do all sorts of weird stuff. That's just saying they're going to be recoiling and doing lots of things. And we say the word ion because it's going to be also the ion, the core of when the electrons leave will also be moving in order to get out of the way for all the other dynamics to happen. Momentum, because like we said, momentum is something key that we look at and use to plot diagrams. And this just basically means how we see it, an ability to visualize what's happening. So here we go. This crazy thing is a setup. So here we have the laser coming in, and here is the gas jet, where the gas jet is what contains our little targets. Then the laser hits the gas jet, and the electrons, we head off to the electron detector. And then the empty ion, after it has been depleted with all of its electrons, heads off to the ion detector. So from that, we're able to see that electrons can leave at a certain point, and then the ion is empty at a certain time. And we use magnets in order to draw the correct things to the correct places. So here's another one on its side. It's essentially the same setup, but just with a little bit more information. So here, once again, we have the laser coming in, we have the gas, we then have, this is circular polarized, we then have a second and first electron from the interaction, and then here we have the ion being drawn by magnets. So that's all I can tell you about cold trims. They produce the same data as us, where we're able to plot them into diagrams and do comparisons, but I can't tell you the ins and outs. I can tell you the frustrations, I can tell you secondhand what it's like to be an experimentalist, but that's, unfortunately, I'm a theorist. But you know, it's okay, you know, you don't have to know everything. So I'm gonna stop talking at you, and now I can talk with you and answer some questions if you have any. You can follow me on Twitter. I do, like I said, I talk about my research on Twitter. At the moment, I'm not using Twitter because I'm finishing off my thesis and I need no distraction from social media. And here is a recent paper and a recent research video if you want to know more specifically about some of the results that I have found. So anyway, thank you so much for listening.